let's go ahead. So welcome one and all to the NYU AI School. Let's jump into a couple of logistics for the school. So there is a Google group that you should be a part of. If not, you can always request access and we'll approve you. It should be in the welcome email. There is a Discord server that I think most of you are aware of and have been actively participating in, which is awesome. If there are any issues, whether those are technical, whether those are non-technical, please feel free to DM the organizers on Discord. We have the admin tags, so you can tag admin, especially on technical issues for questions. There will be an announcement made every morning with links for the rest of the day. So in case you have an issue with accessing links on Google Calendar or otherwise, you will always get an email in the morning, or you can always ask questions about what the day schedule is like. The lectures are meant to be recorded. So we will be recording the lectures, although we will be putting them out only at the end of the week because there is some bandwidth issues. The office hours and labs will not be recorded. So in case you are you have a choice, in case you have limited time, we would strongly recommend you review the lectures that are recorded and put up from last year, which are not the same but similar on similar topics. And then please attend the labs and office hours because those will not be recorded. This year, the office hours are also meant for unstructured discussions. So it's not just that you have to have attended the lab to go to the office hours. We have grad students as TAs who have had some experiences that most of you could probably benefit from. And especially who will be able to answer a lot of the questions you might have, which are outside of the scope of the school. For instance, your personal career related questions and questions about how to start research projects and stuff like that. So feel free to attend office hours. The panels, we have 2 panels this week. We have 3 panels technically this week. The first one will be the ML careers panel. The second one will be the bumpy road to AI research panel. And the third one will be an AMA with grad students. For the first 2 panels, you are strongly recommended to post questions. We will post details of who the panelists are and what the panels are about on Discord shortly, and create separate channels for it. But feel free to pre-post your questions in the respective chat so that we can keep track of them and probably ask the panelists those questions on a priority basis. The lectures are typically from 10 a.m. to 11:30 a.m. Eastern Standard Time. So that's New York time. You will have to convert that to your time zone. And the labs are typically from 1 to 3 p.m. We have lunch office hours where we will have grad students available to discuss more or less anything related to AI research with you. And we have 2 tracks for labs, and we have multiple sessions for each track. So as you, for most of you have seen the Discord and Google group messages, you have been assigned to a certain track. Those are not binding on you. At the same time, since you requested a certain track, we put you in that track. Please ensure that you have access to a Google Colab, which is, if you have a Gmail account, you probably do. We will be using Python and PyTorch for the labs. For the beginner sessions, we will start from scratch. We will give you the basics. For the advanced track, we will go a little faster and probably teach you a bit more detailed concepts. At the same time, the syllabus covered in both of the labs is more or less the same, and it will all be released at the end of the school. I think I've been through all of the things I wanted to go through. And with that said, I will hand over, I will pause in case I missed something and the organizers want to correct me. Yes, you can switch the lab tracks. Cool. With that said, I'll hand over to Savannah. I'll hand over to Katrina, who will introduce our speaker for the day. Thank you so much.
Hi, everyone, and like happy day 1 of the AI school. It is my great pleasure to introduce our first lecturer for today. So we are very honored to have Savannah Theis, who will be giving the lecture on Intro to AI. She is a postdoctoral researcher at Princeton University, working on the intersection of AI and machine learning and physics. And she's also an advocate for AI ethics, and in particular, algorithmic interpretability. And among many other things, she's also the director at the Women in Machine Learning organization. So we're very excited to have her as a speaker. And without further ado, Savannah, the floor is yours.
Great, thank you. Just a second to set up. I can't turn, I don't know if I'm supposed to have my video on, but I can't turn it on.
Let me look into that real quick.
Awesome. Great. Just get my slides. Okay, can you see the slides okay?
Yes, I can see them.
Okay, great. Awesome. So yeah, thank you for that introduction. I'm really excited to be giving this first lecture today, Introduction to Machine Learning. I'll try to monitor the chat as much as possible. So feel free to ask questions in the Zoom chat or the Zoom Q&A. I'll also try to take pauses during the lecture for questions as well. So first, yeah, a quick intro to who I am. My background is originally in physics. So I did a PhD in computational particle physics, where I developed machine learning methods for processing data at the Large Hadron Collider, which is a big particle accelerator. So really at the intersection of data science, machine learning, and physics. And I'm now a research scientist at Princeton, doing, like Katrina mentioned, research in several different areas. So physics informed machine learning, like how we can teach algorithms about physics information that we already know, algorithmic interpretability and robustness, how we can make sure that the systems that we're building are trustworthy and understandable by humans, regulation of emerging technology. So, how we can kind of govern these systems and make sure they're used fairly and equitably. And then some machine learning for social good and community-based data advocacy, trying to use this technology to have a positive impact. So a quick outline of the talk, I'm going to go through a kind of history of artificial intelligence. How do we kind of think about these systems, and how did we get to where we're at today? Introduction to some machine learning concepts. You'll dive deeper into a lot of these topics in the later lectures. So I'm going to just do a quick kind of primer to help get ready for that. And then I'll introduce two really common areas that, again, you're going to focus on later in the school in the next couple of days. So we'll talk about computer vision and natural language processing. And then I'll talk a bit about the state of machine learning today, what kind of questions still exist, ways that you can get involved in this space, and kind of where we see the field going next. Yeah, so really excited to get started with this. So first, a kind of history of AI and kind of how we got where we are today. First, some quick caveats and framing. caveats for kind of this history. The history that I've put together here is really focused on innovations that led to the development of neural networks, which are a certain kind of machine learning algorithm, like we'll see, and they're used very widely today and form the basis of a lot of the technology that we interact with. But there are lots of other kinds of machine learning algorithms as well, and you'll talk about some of those in the course. So this is a selected history. It's focused on neural networks. It's also, totally incomplete. There are other important discoveries and developments and people that I don't have time to mention here. So just keeping that in mind. And then something to kind of keep in mind as we go through this history is also just how computers work. So computers generally take some kind of input and programmatically produce outputs. And these inputs and outputs have to be, at least currently, numerical in some way because computers operate in binary. So we have to be able to encode the inputs and outputs that we want to work with numerically. So that kind of shapes how we think about the history of technological development and the ways that machine learning and AI have developed. So kind of keeping that in mind, before I get started with the real history, I kind of have some questions to consider before we dive into this. So like, what is intelligence? How would you define that? What do you think artificial intelligence means? How could we determine if a system, if a computer is intelligent? And then based on kind of what we know about how computers work, that we have to represent data numerically, they programmatically kind of produce outputs. How could we use computers to solve what we consider intelligence-based tasks? So I'll have these kind of questions like throughout the talk. So feel free to share thoughts in the chat or just kind of, think about these to yourself to kind of frame the discussion. So I'll pause for a second to see if there are anyone wants to share thoughts in the chat about how we might define intelligence or artificial intelligence. Yeah, I see recognizing patterns. Intelligence would be the ability to make a correct choice by considering the scenario. Yeah, I really like that. Yeah, awesome. Feel free to continue to share thoughts. I love seeing y'all's insight, and I always learn a lot from this. Intelligence is hard to define because there's different types of intelligence according to psychology. Totally, and we'll see that how that plays into like how we evaluate these systems as we keep going in the lecture. Is Skynet an appropriate response? Skynet is definitely an example of AI. Luckily, we have not actually built something like that in real life yet. So, but that is definitely an example of AI. The ability to retain and apply information, I think that's a great definition of intelligence. Memory and decision-making, formulate complex thoughts from information, recognize past mistakes and make better decisions off of this. Yeah, really, really awesome answers, everyone. And I think they're all correct. And I think we'll kind of see how these play into like how we design these kind of systems as we keep going. So yeah, thank you for sharing your thoughts. I always learn a lot from asking these kind of questions in my classes. So thank you. All right, so let's dive into some history. So I'm starting way back in the 1600s with something called the mechanical adder, which was one of the first efforts by people to really automate data processing. So it used a system of gears and wheels to do addition and subtraction of small numbers, and you could also multiply and divide by just repeating those addition and subtraction functions. And as I go through this history, I've kind of highlighted some of the different backgrounds of the people that were involved in developing these different technologies to kind of emphasize how many different perspectives were really required to get us to the point that we're at in machine learning and AI now. So this particular mechanical adder was invented by Blaise Pascal, who was a mathematician and a philosopher, and it was an effort to reduce the human effort necessary for tax supervision that tax collectors had to do. So we wanted to make it easier for those people to do their job, which is one of the main motivations for developing AI in the first place. And we'll kind of see that theme repeated throughout the history that I go over. So the next kind of key innovation was the first example of kind of data storage. So you might not think, a loom to weave fabric has to do with the history of AI, but we generally consider this Jacquard's loom, invented by Joseph Maria Jacquard, who is a weaver, as one of the first examples of data storage. So this system used metal punch cards, which you can see here in this image, to actually physically position the threads. And then a collection of these cards would code a program that directed the loom. And this was one of the first systems that enabled consistent results to be repeated over and over again. And this punch card system was actually used as a way of inputting data to a lot of computing systems, even into the 1900s, the late 1900s. Punch cards have been a very common data storage method. So this was a very important innovation in kind of the history of computing. Then continuing through the 1800s, we have the invention of Boolean Logic, which was really key to developing modern computers. So Boolean logic represents logical and true-false reasoning with these things called Boolean operators, and, or nor. And so these form the basis of how computers operate. So and combines things. So if both inputs are true, then the output will be true. If one of them is false, the output will be false. Or is if either one of the inputs is true, the output will be true, and then not just negates the input. So these are really simple logical functions that can be represented in binary 0 or 1, and they form the foundation of how modern computers operate today. And they were invented by George Boole, who they're named after, who was a mathematician and a philosopher. And then later on in the 1800s, we see the development of more mechanical statistical systems. So kind of an advanced version of that mechanical adder that we saw previously. So it combined that punch card technology from the loom with mechanical calculator technology to do rapid statistics. And this was really the beginning, or considered the beginning, of kind of the data processing industry, where you could store data sets and then kind of automatically perform different types of computations on them. And this was again developed in an effort to make some data intensive systems easier for humans. So this was developed in part to help with census data processing, because I think I forget which census it was, but it took like 8 years to process the data from the US Census before this kind of machine was invented. So almost the entire period between one census and the next census in the US was just spent processing the data. So that really motivated the development of this kind of system. So another really key event in the development of AI was World War I and World War II, which really spurred a lot of interest in computing and enabled different technological advances. So particularly cryptography or code breaking was a really key research area during World War II in particular. And this was, again, a very mathematically complex process that involved a lot of different calculations. It was very difficult or impossible to do by hand. So inspired a lot of computer system development, again, to try to ease those kind of calculations and make it easier for humans to work on this task. This inspired a lot of technological innovation as well to kind of support these systems. Vacuum tubes form the basis of the first kind of modern computing systems. And then we transitioned to other types of technology like transistors, which are still kind of the basis of computing hardware today. Kind of throughout this period of really rapid development in both the hardware and the software, this kind of spurred interest more broadly in creating machines that could try to emulate human intelligence. So another key thing that was kind of happening at the same time was different types of scientists were starting to develop more mathematical models of how human cognition works. So when we're kind of thinking about the history of machine learning and AI, we tend to mention two really key innovations. So first is this guy, Walter Pitts, who was a logician, and Warren McCulloch, who was a neuroscientist, developed a mathematical theory of how individual neurons in the brain might operate. So an example of their model of the neuron is up here, right? It takes some set of inputs, which could be external stimuli or messages from other neurons. They're kind of processed through mathematical functions to produce a binary output that would be passed along to kind of tell the person what to do. And they proposed a combination of mathematics and then algorithmic decision making that they thought would be able to mimic human thought processes. So this was totally theoretical. They didn't implement it in any kind of computing system, but it kind of laid the mathematical foundation for modern machine learning, as we'll see. And then similarly, in 1949, Donald Hebb, who is a psychologist, published this book, The Organization of Behavior, which is one of the kind of important foundational texts in machine learning and artificial intelligence that kind of introduced, again, mathematical theories of how behavior emerged from neuron excitement and message passing and brain structure. So how these kind of individual neurons that Pitts and McCulloch modeled could be used together to give rise to more complex behavior, and they could communicate with each other. So I see a question. Essentially, it was at this point when we really gave the computer a sort of brain, correct? Yeah, so I would say we're not quite there yet. This is still kind of laying the foundation for that. So we're just right now starting to model mathematically human cognition, and we haven't necessarily put that into a computer yet. But yeah, great question. Great, and yeah, feel free to continue asking questions in the chat. Thanks for that. All right, so we have we have a lot of technological innovation in terms of computers and algorithms. We're starting to develop a mathematical model of cognition. Yeah, these things combined, going the wrong way, started laying the foundation for what we consider machine learning today. So another really important innovation that happened along the same time was something called the Turing Test. So Alan Turing, who is a mathematician, was really key in some of those efforts I mentioned during World War II to help with code breaking. And he really predicted the development of kind of modern machine learning in 1947. And that eventually computers that tried to mimic human behavior would become really ubiquitous and have a big impact on the world. And he even predicted how it would kind of affect industry and different things. So he developed this thing that we refer to as the Turing Test, but he actually called the imitation game, which is a method to determine if a computer system has human-like intelligence or not. So the way this test happens is there's a human questioner, and then there are two respondents, a machine respondent and a human respondent. And if the questioner cannot determine after some fixed period of time, people often talk about 5 to 10 minutes, if after that time has elapsed, if the questioner can't determine which of the respondents is a computer and which is a human, then it's said that the computer has passed the Turing test, and we would consider that an intelligent system. So far, there's been only one rather controversial program that's been considered to pass the Turing test. And it was a really interesting example. It was a chatbot that posed as a 13-year-old Ukrainian boy who spoke English as a second language. So this introduces some really interesting ideas about, the chatbot is posing as a young person who speaks English as a second language, meaning that you would expect it to make some errors. So it kind of bakes its imperfections into the kind of persona that it's taking on. So if it makes mistakes, you could attribute it to some like real world factors, that maybe English is the second language or things like that. So that's why it's a bit controversial that people say that this bot passed the Turing test, but it kind of shows some interesting components of the Turing test itself, and maybe some of its limitations in evaluating what intelligence means. Yeah, I see a question. It's not really concrete, or it's subjective. Yeah, exactly. So it's really just evaluating if you can if a machine can trick a human into thinking that it's a human. So it's absolutely subjective. And you can kind of get around that a bit by having multiple people do it, so it has to trick people the majority of the time or something. But yes, it is subjective. And this is, yes, I see two questions about like, now we get asked on websites if we are human. So yeah, it's kind of similar. So that is generally done because you can really, a lot of people can run programs now that just like automatically interact with websites. So this can be used, people use it a lot to like buy tickets for a really popular event automatically, or to do web scraping or different kinds of things. So that's often why we get those "Are you a human?" questions on websites, to try to prevent kind of automated behavior like that. So it was human assigned. Sorry, there was a question of if the computer chose the persona, or it was designed. So yes, the system designers chose the persona. So again, that's part of kind of the controversy of this passing the Turing test. Like, some people disagree that it passed the Turing test because, right, the machine didn't decide this is the way that I'm going to trick people. It was set up by humans. And sorry, just checking questions. So yeah, great. This is a great point. Humans' accuracy isn't 100% also. Yeah, so that is, I think, a really interesting kind of facet of the Turing test is right. Human behavior isn't perfect. Human intelligence isn't perfect. So does that kind of bake error into our evaluation of intelligent systems, and what kind of limits does that pose? Like, do we really want to build machine systems that are imperfect if we could have it do a task perfectly instead? Like, does it make sense to base our definition of intelligence on human behavior, or is there kind of a broader definition that we could come up with? Yeah, so I think the Turing test is a really interesting way of evaluating these systems that, you know, is not the end all be all. Like, it is a very famous evaluation metric, and a lot of researchers do try to build systems specifically to pass the Turing test. But I think what we're seeing from a lot of these questions is that it is limited, and there may be other ways of evaluating intelligence as well. All right, I'm going to keep going for now, but please, yeah, keep asking questions in the chat. All right, so kind of post World War II, in the 1950s and beyond, we start to see ways of using these kind of hardware innovations that we've had and these computing innovations that we've had to build intelligent systems in different ways. So a really common one that was used was something called symbolic approaches. And symbolic AI kind of has two key components. There's a logic component that is all hand-coded that specifies a knowledge base based on human intelligence that could be used in problem solving. So this could be a set of like rules that humans know. It could define the space of solutions that are allowed based on some kind of expert knowledge. And then there's a control component that determines how to make inferences and solve problems using that knowledge base that we've hand coded. And so a really famous example of people using symbolic AI in really impressive ways is in 1953, Arthur Samuel used symbolic AI to play championship level checkers. So he actually coded a computer that could play checkers very well, and it worked with the symbolic AI approach. So he defined the space of possible moves based on the structure of the board and the way that checkers are allowed to move, how many pieces start out, all of those things. So he encoded all of that by hand. That was the logic component. And then it kind of used this pruning structure to determine the chances of winning with each possible move. So based on the configuration of the board at the time that it was going to make the computer was the next move, and based on those rules that Arthur had given it about how this works, look at the base of music and probability of winning, and what to do based on the highest probability of winning. And this is widely considered the first example of a real learning program. All right, sorry, I'm lagging. I don't, yeah,
I think
it's my
you're
internet.
all right now.
Okay. So yes, this is widely considered like the first example of a real computer learning program. So yes, it's kind of a decision tree, exactly. All right, awesome. So another kind of key event that happened in this post-World War II era was this Dartmouth Workshop. So like I mentioned, World War II and the surrounding efforts really prompted a lot of interest in intelligent machines. And so in 1956, there was this really famous workshop that brought together different mathematicians, scientists, and engineers for 2 months to kind of explore the mathematical foundations of intelligence and how we could design computer systems to try to mimic that intelligence. And this is considered kind of the birthplace of AI, artificial intelligence, as a field of study. They, say that the work the kind of phrase artificial intelligence was really coined at this workshop. So it's kind of the birthplace of this as an academic field of study. And their efforts here were really based on this conjecture that I find very interesting, that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. So I find this really interesting because even today in 2022, we don't have a mathematical model of our own cognition yet. We have some idea how the brain works. We have those mathematical models of neurons that we talked about. We have, kind of brain mapping from MRIs and different kinds of things. But this was really a kind of big statement to make in the 50s. We mathematically describe every facet of thing. Like that's a big statement that they didn't necessarily have it up. That kind of framed how we think about AI and machine learning as a field. To kind of define themes that would guide the field moving forward. So things like wanting systems to do language processing, a focus on neural networks, so computations based on the way the human brain works, the need for abstraction and creativity in truly intelligent systems, and lots of other themes that would really kind of define the way people approach this work in the future. All right, so again, kind of at the same time, a bit after this workshop and in the 60s, we had some really key algorithmic developments, called perceptrons, which really formed the basis of modern neural networks. So perceptrons were a type of algorithm that combined Hebb's model of neural cognition systems that we talked about, that mathematical model of brain neurons, with Arthur Samuels and other work on symbolic AI to create a neuron-based learning model. So each neuron in this model, which mimics human brain neurons, has adjustable parameters. So it has these different weights, W's up here. So you would have a piece of information coming in. They would be modified by some weights, and then that would determine the output of the neuron. So a similar structure to how human neurons work, but all of these parameters are adjustable. And learning or training a neuron is the process of adjusting those parameters to a certain task and data set. So to help this neuron work with certain types of data to do a certain task. So generally, and so this is an individual. They are to
There's a little bit of a disruption again. Sorry for the interruption. Savannah, there was a bit of a lag here for the past like 20 seconds.
Okay. Okay, so I was going to say.
Sorry for the disruption, guys. I think Savannah will be back in a moment. Hey, I think you're muted.
Okay, let me try turning off my camera, maybe.
Yeah, maybe we can do that. Thank you.
All right, so these neurons, these mathematical.
I believe the slides are not up. There you go. Thank you.
Okay, so these mathematical neurons can be grouped together into into layers. So you can have multiple adjustable neurons, and then you can also stack those layers together, which is kind of what's shown in this second diagram down here. So you have an input layer where data is first processed through. Those neurons produce an output, which is passed on to the next set of neurons, and that can continue on to produce the final output for your task. So generally perceptrons as a network aim to learn a function that maps your inputs, which are the features of your data set, to outputs, which are some type of predictions. So, a simple example could be if I have data about a plant, like I have maybe the height of the plant, the number of leaves that it has, and the length of its roots, some different set of features. I could process that through a perceptron to, predict the type of plant that it is. So if I'm trying to distinguish between, 3 different types of plants, my input would be those features of the plant, and my output would be what type of plant it is. And so the goal of the perceptron network would be to learn a function that maps those input features to output features by approximating that function with these adjustable weights. So we try to vary those weights so that this whole network starts to approximate that true function that maps plant features to plant classification. So we saw really key innovations in developing these perceptrons in the 50s and 60s. So the first kind of single layer functional perceptron was invented by Frank Rosenblatt, a psychologist, in 1957. It was only a single layer, so it could only learn a very small set of functions, and particularly it could only learn linear functions because it only had one set of weights, so it could only transform the input data linearly. The next innovation was in 1965, where these 2 mathematicians developed a multi-layer perceptron that could learn more complex functions. So instead of just learning linear transformations, it could learn more difficult transformations. So it could solve a wider class of problems. And they also developed a method to start to tune these weights effectively and set to approximate different types of functions. We had these examples of perceptrons or neural networks, but during the kind of rest of the 1900s, they were still kind of one-off successes. It was hard to build very large networks, and it was hard to know how to adjust the weights. So it was really kind of limited in the types of functions that those perceptrons or neural networks could approximate. So they couldn't be applied to that many types of problems. So there were different efforts to try to build intelligent systems in other ways. So there were developments of different pattern recognition algorithms that compared new data points or samples to existing data. For example, the nearest neighbor models, which is what's shown in this diagram up here, where if you're given a new piece of data, you look at the other pieces of data that are closest to it and use that to determine what label you'll give this new piece of data. So if we were trying to classify this green circle, we would look at like what's nearest to it. So if we consider the 3 nearest neighbors, we have 2 triangles and 1 square. So we would, in that case, give the green circle a triangle label. But if we considered more neighbors going out farther, we then would have 3 squares and 2 triangles, so we might give it a label of a square. So developing different kinds of algorithms to do like automated data labeling, to learn about data distributions, Continuing that kind of symbolic or AI approach with the kind of expert systems. So for example, developing chatbots with like fixed vocabulary that you encoded beforehand, and it would kind of just give the appropriate response based on keyword detection. Explanation-based learning, which tried to, again, it relied on these specified domain rules and tried to discard non-relevant data to limit the function space that it was looking over. So this was a way that people kind of took the symbolic approach that Arthur Samuels used for playing checkers and applied it to a more complicated system like playing chess, where there's a lot more moves you could make. So you need some way to limit the space of moves that it's evaluating the probability over. And then there were some more examples of successful neural networks for very specific tasks. So for example, this NetTalk algorithm kind of learned to speak English by learning to map words to phonetic sounds. So you could feed it a string of letters and it would try to predict how it would sound phonetically based on other examples that had been shown. So there was different work going on, a lot of different approaches, but it wasn't, hugely successful until there was some.
Sorry, there is one question from the audience.
On. Okay, so for explanation-based learning, the way of thinking when playing chess is almost identical to the programmer themselves. Well, I guess I don't know how people play chess, I guess. So I guess we would have to ask an expert chess player, but I guess probably kind of like you think through possible moves you could make and try to evaluate the probability of winning. The reason that machines are often more powerful than human players is that they can really evaluate the full space of possible moves. So maybe there's some that a human chess player wouldn't come up with that are just like really kind of rare moves, but could have a big chance of winning that a human player might not come up with. So that's kind of why machines can do a better job, because they're able to evaluate like the very full space. All right, so in the 80s and 90s, there were some really key innovations in optimization methods that were used to that helped us use neural networks more efficiently to start to solve more types of problems. So in particular, I highlight two really important ones here. So backpropagation is the algorithm that was developed to use training errors to progressively adjust neuron weights and improve the model fit. So you would send a piece of data through your neural network, have it processed through all those parameters in your hidden layers, get some output prediction, compare that to the truth value, and then progressively use those errors to adjust first the first hidden layer, and then the next hidden layer, and so on, back through to the beginning of the network. And then in the late 90s, there was a big innovation in gradient-based learning, which was basically a way that you can effectively do this backpropagation on computers. So it made it easier to do the calculations to know how much to adjust to the weights of those hidden layers. So the combination of these two innovations, along with increases in computing power and data storage, having more memory available, more processing power, greatly expanded the space of functions that neural networks could learn. So this is what really enabled the kind of current state of machine learning that we have right now. So in the 2000s, we've really seen a extremely rapid growth, and particularly even in the last 5 to 10 years of neural network-based machine learning. So now we've seen neural networks applied successfully to a ton of different problem spaces, to image processing, to sequence data, even generating new types of data. And we'll talk about these, you'll learn about some of these different neural networks in more detail throughout the rest of the class. But this really opened up the power of neural networks and made machine learning into the very popular field that it is today. Along with one more key innovation that I'll mention is kind of the availability of GPUs, which enable really deep models, so tons and tons of layers in that neural network, and allows those to be efficiently trained. And today, machine learning is used across almost all domains. I've listed a bunch of examples here: cancer detection, playing games, facial recognition, generating text, search and newsfeed curation, decision-making, trend forecasting, all kinds of different things. There's many, many more. So this is a really now powerful technology. What's the fundamental difference between artificial intelligence and machine learning? Great question. So I talk about that in a few slides, but I can go ahead and answer it now. So artificial intelligence is a bit broader than machine learning. So machine learning is kind of this approach of finding patterns in data sets without those patterns having to be explicitly stated. So it's a certain way of encoding intelligence into computers, but artificial intelligence encompasses a lot more than just that. So it could include things like actually designing the robotics, developing sensors that can take in visual information in real time, things like that. So it's not just the machine learning neural network part. Great question. How much faster can artificial neural networks process data than our own brains? So that's an interesting question. So I wouldn't say that it can necessarily process data faster. Like, we can make inference. It depends on the task. Like, humans can make inferences very quickly once we know how to do something. So like, once you know what a cat looks like, you kind of instantly recognize when you see a new cat that it's a cat. But kind of the advantage of machine learning is that it can, in some cases, learn more quickly than humans. So in particular, with really big data sets where we don't necessarily know the patterns that we're looking for in those data sets, that's really where machine learning can kind of outperform humans. So things like the playing chess example we talked about, we can't necessarily compute the phase space of all possible chess moves, whereas a computer can. So it's kind of certain tasks and things where it really outperforms humans. So we will talk about the training process for machine learning models in a few minutes. Thanks for that question. All right, so I'm going to do a quick interlude with some more kind of brainstorming questions before we kind of go on to some of the basics of machine learning. So some of these we kind of already talked about, like, does it make sense to base our evaluation of artificial intelligence on how we understand human intelligence? Are there other ways we could do that evaluation? Does it make sense that we have based pretty much all of our modern machine learning algorithms on the physical structure of the brain, like trying to mimic these actual neurons in the human brain and do that with a computer? If a system can solve a really complex problem, but we don't understand how it solved it, do we still consider that intelligent? And then we talked about this a bit. Our errors or imperfections essential to human-like cognition? How does this relate to the Turing test? Is that a really good evaluation of intelligence or not? So yeah, would love to hear any thoughts on those questions. Yeah, so the brain is full of neural pathways. So that's how we base our algorithms. The more we understand the human brain, the more accurate our models get. Yeah, so I mean, that's a possibility, I think, is what I'm trying to get at here. It is, yeah, absolutely. Maybe we understand more about the brain. We're better to build better neural-based models, but perhaps there's other ways that we can model data as well. That's not based on how the human brain works. There's other types of intelligence in the world. Different types of animals have different kind of visual pathways. They can take in different types of information than we can. So it's possible that there's other types of ways of designing intelligent systems as well. Could be a good baseline to work from. Yeah, absolutely. I mean, it has been a good baseline to work from so far. Absolutely, we've seen neural networks can be extremely powerful. Errors and imperfections created by AI are usually man-made errors or errors that are programmed to happen with the AI. AI can't make those kind of mistakes genuinely. Yeah, that's a really interesting point, and we'll see that come up again when we talk about kind of bias in AI systems and other types of mistakes that it can make. Yeah, it is often because it's just copying what humans do. Yeah, awesome. Yeah, it makes sense to base machine learning on the brain, as the brain can store a lot of data, but these algorithms can go through them faster. Yeah, absolutely. Are we too far from making AI that's able to analyze and improve other AIs? Yeah, so there's some really interesting work happening in that space right now of developing AIs that can write code that actually runs on computers. It's not super effective yet, but that's definitely a space of research. Yeah, awesome. Thanks, guys. I'm gonna continue going just in the interest of time, but really awesome questions and insights. All right, so I'm gonna just talk about a couple kind of key foundations of how we do modern machine learning, and you'll hear more about these in the future lectures. But right, kind of just to give us a definition of machine learning, like I mentioned, there's a lot of different ways that people kind of define it that are pretty similar. The one that I tend to use is this one in bold, using statistics to find patterns in large data sets without those patterns having to be explicitly stated. So this emphasizes the need for data in machine learning. We can't have machine learning without data, at least in our current, the current way that we do machine learning. And then it highlights that, the kind of key innovation and the exciting thing about machine learning is that we don't have to tell the computer exactly what to do. It can adjust itself based on the data that we show it. So yeah, we talked about this a bit already, but a lot of modern day machine learning is neural network based. Particularly, there's been a focus on what we call deep networks with lots of layers. You might have heard the phrase deep learning. So this is a nice diagram that kind of describes how these fields fit together. So like we mentioned, artificial intelligence is kind of this big bubble that encompasses both machine learning, but also lots of other things like robotics and other kind of aspects of intelligence. Deep learning is then, again, a subfield of machine learning that's very powerful and has been the focus of a lot of research recently, but there are lots of other algorithms in machine learning. And then data science kind of intersects with those three areas because, like I mentioned, we need data to train machine learning models. But again, there's things you can do with data. There's types of data science that are not machine learning, deterministic models, statistics that are not necessarily machine learning based. And then big data kind of intersects deep learning and data science in particular, because generally the deeper your models are, the more data you need to train them, because you have more parameters that you have to learn. So you need more examples to help effectively adjust those parameters. Right, a lot of the most powerful algorithms that we have today require extremely large data sets to train. This can raise concerns around data collection. How do we get that data? How do we store it? How do we determine what it's used for? How do we make sure that the data is robust, it doesn't change over time, things like that. And then I also want to highlight that machine learning really intersects with a lot of other fields. There's some examples down here, scientific machine learning, so using machine learning in science and engineering, language processing, computational health, robotics, privacy and ethics. So we really need people of all types of backgrounds, both life backgrounds and academic backgrounds, to continue to innovate in this field and to make sure we do that innovation responsibly. So here are just some examples of types of problems that we can solve with machine learning. So the probably two most common ones that we talk about are classification and regression. So classification is where we're trying to predict a class label for an input. So an example is spam detection. So your input would be the text of an email and maybe who sent it, when they sent it, things like that. And the machine learning model would predict a label, either it's spam or it's not spam, and that would determine where your email server puts the message. Regression is the other probably most common type of problem we do with machine learning, where instead of predicting a specific label, we're just predicting a continuous variable. So the example I have here is predicting home price. So you have features about a house, maybe like the number of bedrooms, the age of the home, the school district, things like that, and your machine learning model would predict the selling price. There's also lots of other things we can do with machine learning. We can do clustering, where we just try to group similar inputs together without giving them a label or a prediction. We can generate new data based on some pattern that the algorithm has learned about. We can identify common rules and associations in data. We can rank and order data based on how users interact with it. We can try to detect anomalies or abnormal behavior in data distributions, again, by learning about the distributions and the pattern in the data. And we can also learn new representations of data that can help us do other tasks better. So the kind of underlying thing for all of these different applications is that we need to learn about the distribution of the data that the algorithm is shown. And then the information that it learns about that data distribution can be used to do all different kinds of tasks. And then I want to just briefly mention, I think this course is generally focused on supervised machine learning. So we talk about two different kinds of machine learning pretty often. So there's supervised learning, where the model is provided with labels and the algorithm tries to learn the relationship between the input features and those labels during training. So that's the way that neural networks work. Where we're using that neural network structure to do classification or regression or other types of tasks. There's also unsupervised learning, where you don't have any labels or classification, and you're just trying to learn about patterns that exist in the data. You're not saying what specifically you need to use those patterns to do. You're just interested in the structure of your data. There's also reinforcement learning, which is another type of machine learning, where models are rewarded for meeting goals. But I believe the focus of this course is primarily supervised learning. So how do you reward a model? So basically you just write a mathematical function that will become like more positive if the model behaves the way you want it to, and more negative if it doesn't. So this can be used to do things like training a robot to walk through some like course with objects in the way or something. So the reward function would become more positive the closer the robot gets to like the finish line, and it would become more negative as it is farther away from the finish line. And so it learns a behavior to like navigate the course to try to maximize the reward function. That's a very simple example, but that's kind of how that works. A couple other questions. Gmail grouping emails into primary, social, marketing, etc. is machine learning? Yes, absolutely. So machine learning, I am sure that you've interacted with machine learning algorithms like at least 5 times already today. Pretty much every piece of technology that we interact with has machine learning underscoring it. And then is this how companies like Facebook predict the personality and traits of their users through data? So that's a really interesting question. This is how they do that, yes, but they're not actually there. So sorry, I'm trying to think about how to answer this question. I really like this question because they're not actually predicting personality traits. We don't have a like machine learning model that can do that because we don't have a mathematical model of personality traits, and they don't have like truth information. So they might predict something that they say is like a personality trait, but really it's just an approximation of that. So Facebook like cannot actually learn about you, you know, in a real sense, because we don't have a mathematical model of those things. So like there's been some work where people people say they build an algorithm to like determine someone's trustworthiness. But in reality, we don't have a way of mathematically measuring trustworthiness. So you're approximating something that we've decided is like a proxy for trustworthiness, but it's not actually that. So yeah, really interesting question. This is the kind of algorithms that they would use to do that, but I think it's important to consider like what the limitations of machine learning are. How do we choose between different machine learning algorithms? So we'll see, you know, in the rest of this talk and in the rest of the week, different algorithms tend to be suited for different types of data and different types of problems. So that can help you decide which ones to use. Cable companies use machine learning for digital media, advertising, cable trafficking. Yeah, so advertising uses a ton of machine learning and data science to try to show ads to the people who are most likely to buy a certain item. Ad targeting is a huge area of machine learning applications. Also, yeah, web traffic routing is another one. How often do we use Gaussian distribution or normal distribution in AI and machine learning? I'm not exactly sure how to answer that. We try to learn about different distributions of data, and in some cases we assume that data follows a normal distribution or a Gaussian distribution, but we also try to learn when it varies from that. Awesome. And let's see, going back to the questions posed before, I think a caveat of modeling AI of human behavior and intelligence is just as humans have societal preconceptions and bias, we can also end up training AI models with biased data. How do we ensure that we use machine learning and AI models without bias? Great question. And yes, I have some slides on this later on. This is absolutely a huge concern, and we have seen repeatedly that this is exactly what happens if we train machines to just mimic human behavior, because humans are biased and we see those biases reproduced and scaled up. And there are different ways to address this. And I'll talk about some of those hopefully in this talk. There's also a great talk from Emily Denton on Friday, where she'll dive into a lot more of these issues, but you are absolutely spot on that that kind of behavior happens a lot. Awesome. All right, I'll keep going. So the way that we actually do this in the supervised learning case is we have our training data set with a bunch of examples of your input features. So each of your training examples would have the same features, and you have a bunch of examples. You choose whatever model you're going to use, and then you optimize the parameters of that model to fit your training data. In the case of neural networks, we do that using those backpropagation and gradient descent algorithms that I mentioned, and I think you'll talk more about how those work mathematically in some future lectures. And then you use that model to make an inference by sending a new piece of data through your trained and adjusted model and seeing what prediction it makes from your new piece of data. And how do we evaluate these models? So typically the first thing that we look at is model accuracy. So just the percentage of correctly predicted samples. But other behaviors matter as well. So things like the number of true and false positives and negatives can be really important. You know, maybe you care about, you know, misclassify, or maybe you care about, yeah, false negatives more than false positives. You care about certain kind of error more than others. You know, if we're trying to detect a disease that's highly contagious, maybe we care more about not missing any cases of the disease than we do about telling people who don't have it, who are healthy, that they have the disease. You know, different types of errors can matter more in different situations. Performance across classes is also important. Maybe, you know, if we're trying to identify different types of we're trying to identify different types of animals, and our model works really well on cats and dogs, but not on fish. All of the errors that it throws are on fish. That's important to know. Stability, does your model work well over time? Does it degrade? Is it robust to small adjustments in your input data? Things like that are all really important to consider. And then one thing that I want to highlight is to make sure a model will generalize well to new samples. We typically do something called a test train split, where you use only a portion of your data, the training set, to do that model parameter adjustment and training, and then you evaluate the performance on the other subset of your data, the test set. And if your data performs well on your training set and poorly on your test set, then you know that your model is not going to work when you deploy it. It's not going to generalize well. It's learned things that are only in your training data set and don't generalize. So we can kind of see an intuitive example of what that looks like over here. So in the case of underfitting, where our model hasn't learned enough, maybe we're trying to separate these circles from squares. And it's just learned a flat line that doesn't do any kind of separation. So that's called underfitting. And we can see this is a loss function plot. So this is showing kind of the error of our model. So in this kind of underfitted regime where it hasn't learned anything, we can see the error is pretty large. And then as our error starts to decrease, we would say probably our optimal solution is around this area where we have a pretty low error rate, the training set accuracy is these orange dots and the test set accuracy is these blue or gray dots. So it's before we start seeing a divergence in the training and test set. So this might be a good solution where we do see the function it's learning is, sorry, I messed up these functions are actually incorrect. Sorry, this slide is a little messed up. This is actually the overtrained function where it's learned a very kind of convoluted function to specifically hit all of the black dots. But if we added a new piece of data that's slightly different, the classification function might not work anymore because it's just memorized specifically these examples that it's showing. So this is, yeah, sorry about the mistake here. I'll fix that before I upload the slides. But right, we can check for overfitting by kind of seeing how the training and test set performance diverges. I'm going to skip this demo since I'm running low on time. But when the slides are uploaded, you can go to this link or just remember TensorFlow Playground. And it's a really cool kind of intuitive example where you can, without any coding, adjust different neural network designs and see how they work on different data sets and kind of get a sense of how that training and parameter optimization happens. And I see a question, do all models have to be created from scratch or are there models that already exist for specific contexts? Great question. So there are, there are a lot of models that are already trained, particularly for really common tasks like computer vision, image classification, or text processing. There are models that are kind of available already that you can start from, and you can fine tune them a bit for a specific problem, or generally they work well for a lot of tasks already. Yeah, great question. All right. So yeah, kind of knowing a bit more about how machine learning works now, I'm interested if y'all can think of an example of machine learning that you interact with in your daily life. We've already seen some, like we talked about Gmail filters, but maybe think of a different example, and then you can consider, do you think it's a supervised or unsupervised model? What type of data might have been needed to train it? What the learning objective of the model was, and maybe some important considerations during training. Yeah, I see a lot of great answers already. Google search, translators, Facebook ads, Amazon suggestions, Uber, absolutely, recommender systems, Google map routing, Netflix recommendations, totally. Awesome. So let's take one of these examples, maybe of like recommendations. So Netflix recommendations, Amazon suggestions, Facebook ads, those kind of things. What kind of data and model and learning objective might be used for recommendation systems like that? Yeah, previous watches, absolutely. What you've engaged with before. User likes, yeah. Also, yeah, maybe demographics, things like age, browser history, totally. How long you stayed on a video, absolutely. So like user behavior and user features are definitely the kind of data that's used to train those. Any like important considerations that you might want to think about if you were building a recommender system? Privacy, yeah, great. How to evaluate the results, yeah, how do we know if it's meaningful? How do we know if like that's actually what the user wanted, or we just showed them this content and so that's what they're engaging with because it's what we showed them? Yeah, great considerations. Awesome. So I love doing these kind of evaluations all the time. Like if I encounter some kind of machine learning system out in my daily life, I love trying to take it apart like this and think about, what data they might be using to train it, how they might have designed the system. I think this can be a really yeah, interesting way to see how much impact these algorithms have on our lives. Awesome. Okay, so I have like 20 minutes left. So I'll go quickly through some of the rest of the slides. So next I wanted to kind of talk about two really popular areas of machine learning applications. And these are also the ones that you're kind of going to dive deeper into as the week goes on. So I'll give some quick introductions here. So the first one is computer vision. So computer vision is a huge subfield of machine learning, particularly like one of the applications of machine learning that I think we hear talked about a lot is like self-driving cars, which absolutely rely on computer vision to see obstacles around them, other cars, road signs, things like that. But computers see images of giant matrices of pixel values. So for example, in this cat, just this small section of the cat's face is just a ton of individual RGB values for individual pixels. So, we can kind of think about some difficulties that this type of data could present for machine learning applications. So in particular, I highlight a few here. So one of the biggest ones is that if we use just individual pixel values as training features, that's a ton of features to try to learn from. So that can be hard to optimize. But if we try to just do hand engineered features where we just like pick out specific parts of the image to focus on or things like that, that can be hard to generalize. Also transformations. So images, if we're doing object classification, on the left side of an image and on the right side of an image, they're both cats. So we need to understand that like the same object can be translated in space, or it can be rotated and still be the same object. So that can also be difficult for machine learning algorithms to learn. And then complexity, images can be very complex. There can be, different objects in the same image, multiple instances of the same object in an image. So these can be very kind of difficult pieces of data to learn from. But luckily we have some really great innovations in computer vision algorithm design. And again, just like we saw with kind of how regular neural networks developed, researchers in some part took inspiration from human visual biological systems. So sorry, I'm going a bit quickly here, but I know that you will cover this in more detail in the next couple of days. And I want to get to kind of the last part of my talk as well. So sorry, I'm going a bit quickly, but convolutional neural networks are generally the algorithm that we use for image processing. So on just a conceptual level, because again, you'll go more into the math and details later on. These work by convolving a filter or a matrix across the input image to create multiple transformed representations of your input image. And then you use those new representations of your image as input to a standard just neural network like we already talked about. So you basically take one image and you learn these different filters. You apply those filters to the image to get new representations of your image, and then you feed those into a regular neural network. And the convolutions or filters can learn all different types of information from your image. And some of that information is human interpretable, like, these filters up here we can see are kind of learning like outlines, different types of depth information, but convolutions or filters can also learn much more complex information that's maybe not human and interpretable. So as we see, going on to some of the later filters in the neural network and the kind of deeper layers, it's learning these representations of images that, mean nothing to us as humans. They kind of just look like blobs and blurs, but there's some relevant information in here that the computer is extracting from these filters that it can then feed into that final connected neural network layer to make some kind of prediction about the input image. So human visual processing combines lots of different tasks, like classification, locating where an object is in an image, and then deciding what that object is. So there's several difficulties that we have in really mimicking true human vision with artificial intelligence. So in particular, you need a ton of training examples. Like you need an example of every type of object that the system could see. If you just show it examples of cats and dogs, it won't, know what a bird is. So it can require very large data sets to train these systems. There are situations that humans can understand that can be very tricky for AI. So like if objects are partially concealed, it can be very hard for AI to identify what they are. It can struggle with depth or other types of visual distortions. And also models don't have physical intuition, in most cases, objects don't come with physical intuition that humans do, where we kind of understand that the world is like three-dimensional. We have rotation, invariance, and things like that. Those do not come for free with computer vision systems. We have to either show it enough examples that it learns that, or we have to explicitly tell it, which is actually some of the work that I do of how we can bring physical intuition into machine learning algorithms. So you see a question, is that why there was that problem that AI was not detecting certain faces? So that was actually, there's a couple of reasons. For that, the kind of primary reason that we saw for that was going back to this issue of data bias that we talked about, where in training, a lot of facial recognition algorithms were just shown many more examples of white male faces than any other types of faces. So it learned to do a better job on that type of data because that's what it was primarily trained on. But yeah, there also can be vision issues that come into play in that, where like our camera systems actually are designed to work with certain skin tones better than others, and things like that. So that can cause issues in visual processing for AI as well. But primarily, I think what you're talking about was a data bias problem. So computer vision is really powerful, though. It can be used in a ton of different applications. So I've highlighted just a few here. So some really impactful things like detecting different types of crop disease, which can help with addressing things like world hunger, tracking populations of elephants using satellite imagery. It's also used for things like disaster response. There's a lot of work using satellite imagery to do kind of different types of tracking in areas where it can be hard to do on the ground. This down here is an example of cancer detection. So using MRI or other types of medical imaging, doing automatic cancer detection, which could help locate difficult to find cancer that doctors might miss. And then also just like more kind of fun things like, knowing how to apply Snapchat filters. That is AI, so it has to kind of detect facial landmarks in your image so that it knows where to apply the filters, but it can also be used for more kind of sinister things. Like I see someone mention crime detection. It can be used, for different types of surveillance, facial recognition, like we mentioned, tracking, different types of things. So there are, helpful applications, kind of fun applications, also potentially negative applications. Drone operation, absolutely. Automated weapons targeting, Yes, this is used a lot in the military. Deepfakes, yes, deepfakes are a really interesting and very scary area of machine learning that combines computer vision with data generation. So you can actually create videos of people, saying or doing things that they have never done. It's totally computer generated, but it's hyper realistic. So that, yeah, there you can see how this opens up a whole new space of kind of interesting and potentially worrying applications. Yes, so that's what deepfakes are. You can forge something that is undetectable. It's very difficult, or in some cases impossible, to tell deepfakes from real video, which, yes, is very scary. I'm gonna skip over, because I only have like 10 minutes left. I'm gonna skip over this text processing stuff right now, but it will be, you'll talk about it more in a later lecture, and also these slides will be uploaded, so you can check it out if you're interested. But I want to get to just some comments on the state of machine learning work today. And I see some questions. How much machine learning code can be reused in different machine learning applications? Like, how much of computer vision code could be reused when writing a chess AI? So that's a good question. I guess it depends on how you were going to be playing chess. Like if there was a vision component, generally like the software, there's a bunch of software libraries that we use to develop machine learning, and I think you'll see some of those in the labs. And you can use the same kind of functions to write all different kinds of machine learning algorithms, but typically like they'll have to be retrained for each different kinds of things you want to do. Can the training of models on white people affect computer vision models while testing on Black people, like in facial recognition? Yeah, absolutely. And I'll talk about that more in a second. All right. So, we've kind of seen machine learning can do so many different things. It can play games, it can detect cancer, it can classify your emails, it can generate text, it can predict stock prices, and there's many, many more things that it can do. But there are still a lot of known issues, unsolved problems, and open research questions in this space. So it's a really, really exciting field that is continuing to grow. So there's space for many, many more people with diverse perspectives and interests to be involved. And I'm just highlighting here in the last few minutes some areas that I find particularly interesting in kind of ongoing machine learning work. So in particular, a lot of the successful applications of machine learning that we've seen are currently very task specific. So different types of algorithms are built to handle different types of data. Learning to do well on one task doesn't mean that your model will be able to do well on a different type of task. And another thing that I kind of think about a lot is that representations are generally not connected to each other. So if you have a language model, that like learns about writing about birds, and a computer vision model that learns to recognize birds, those things are not necessarily connected. Like we don't necessarily have in machine learning right now an idea of concepts the way that humans do, where we kind of recognize that like a cartoon bird is a bird, a real bird is a bird, like a picture of a bird is a bird, a sentence about a bird is a bird. Those are all the same kind of idea. That doesn't necessarily exist in machine learning right now, but ultimately there is a really big interest in what we call artificial general intelligence, or AGI, that more closely mimics human reasoning and human cognition. And it's not really clear yet how we could get there. Task specific models, like some of the language models or computer vision models that I mentioned are already really large. So it's not clear how we could kind of like bring more tasks together without, you know, making with the computing power that we have right now. And you really need a lot of different kinds of systems, different kinds of information, different kinds of processes to work together to actually mimic human intelligence. So that's kind of what this diagram is showing over here. Like you have, you know, language processing, reactive processing, working memory, long-term memory, emotions, concept of self and others, reinforcement, all these different kinds of processes that really underlie human cognition. And we've done a good job at approximating some of these with machine learning, but not necessarily all of them, and certainly not all of them together. So, you know, this is a huge open area of research is how we can start to bring more of these things together. And then another really, really interesting area, and I think Sarah, who gave this lecture last year for these examples that I borrowed from her slides, is that model sizes, like I mentioned, continue to grow. A lot of the models that we use today are huge. They have a ton of learnable parameters. It takes a ton of data to train them, a ton of computing power. But even with all of that, the relationship between those parameters and how the model actually works is generally not well understood. And we see some really interesting behaviors, particularly like diminishing returns. As we've shown up here with some of those really large models, you need millions more parameters to eke out just small gains. So particularly for this model that I've highlighted up here, you needed to almost double the amount of weights just to improve 2% in accuracy. And that's pretty surprising and pretty inefficient. And particularly other studies have shown there's a lot of redundancies and over parameterization in a lot of machine learning models right now. So you can use a small set of model parameters to predict others. And in some cases, after training a really big model, you can remove a bunch of the parameters from the model and maintain the performance, but you can't necessarily start with a very small model and train it and get the same performance. And we don't understand why that's the case. This is a big, again, open question of research. And, you know, in addition to just understanding machine learning better, there's a real environmental cost to building these big machine learning models, training. I think it's BERT, which is one of the big language models that's used a lot. Training that model one time emits the same amount of carbon dioxide as a transcontinental flight. So there are real environmental impacts of doing this kind of huge model development, giant training. So by trying to understand how these models work better, we can be more efficient, more environmentally friendly. We can build more interpretable models where we really understand the behavior. And that is probably, well, at least I believe that's a better direction for machine learning in the future. Similarly, we often don't understand exactly what information a model is using to make a decision. Even if we try to probe that, like we saw with CNNs and those filters, a lot of the features are not human interpretable. But sometimes there are, you know, known behaviors in the data set that we want to avoid. Maybe we're training a model with historical data, and we know that that historical data is biased, and we don't want our network to exhibit that type of bias. How do we prevent that if we don't understand how the network is leveraging its information? So interpretability is another really important area of research in machine learning. And then, you know, like we've mentioned a few times, there are a lot of known issues with data bias where models are trained on historical data. So in this example, this is a really famous recidivism prediction tool that was used by judges, or is used by judges, to predict who is likely to commit another crime, and that's used to set bail for people. And it's based on data with historical biases based on, like, in the US, which communities we police, how we have sentenced people in the past. We know there's racial bias in all of those aspects. And also the designers of this algorithm didn't test the error across different classes. So in particular, the one type of error, so people who were labeled high risk but then did not commit another crime, that type of error disproportionately affected African Americans. And the other type of error, people who were labeled low risk but did commit another crime, that type of misclassification was predominantly in white people. So we see a very clear racial bias in this algorithm that could have been avoided potentially through different methods, like evaluating the different types of errors before you deployed it and thinking about the history of the data that you're using. So this is another big area of research, is how we can try to prevent these biases, how we collect and use data. And similarly, the way we design systems is also another really interesting area of work. So this, I think, the best example of this is with newsfeed or information curation algorithms. So for instance, how Facebook or Twitter or YouTube decide what content to show you. Like we talked about a bit earlier, typically the primary goal here and the kind of information they use is just keeping people interacting on the platform for as long as possible. So you want to show people things that will keep them around. But this can and has led to kind of unintended behavior. We can think about, ways that an algorithm might surface content that keeps people around but has impacts that we don't want to have in society. So, creating information silos where you click on information that you already agree with, and so the algorithm starts to only show you that information, and maybe you miss out on diverse news sources. And radicalization pipelines. There's a really interesting study on YouTube that shows how the YouTube algorithm would show people more and more extreme content because that's a way of keeping people engaged on the website. And this has very real impacts on people, coming to believe in conspiracy theories and other types of radicalization. Also, this can accelerate the spread of misinformation and on all different kinds of things. And unfortunately, research on some of these behaviors is suppressed by the companies that develop these algorithms. So this is a really, really important space of work as well that I'm sure Emily will talk more about in her lecture. And then finally, the way we deploy these systems is also really important to consider. So an example that I mention a lot that I have here is Rite Aid deployed facial recognition systems only in low-income areas. And this was, nominally to help prevent shoplifting in their stores, but it raises a lot of questions. One, like we mentioned, facial recognition, a lot of these systems have measurable bias. They don't work as well on minorities or women as they do on white males. So that's already an issue with the people who will be experiencing the errors of these systems. But also it raises questions of like privacy as an inherent right or an economic privilege. Like just because you live in a low income area, does that mean that you are forced to consent to surveillance? That maybe more economically privileged areas do not have to consent to, and things like that. And I have some more examples here that I encourage you to look at once the slides are uploaded. So I think I'm a bit over time already, but I think these are some really important questions to kind of consider as we think about continuing to use and develop machine learning. Are we okay with using models that are not interpretable? what issues could arise if we do that? And these are complex questions. So maybe in some cases, it is okay to use models that aren't interpretable. In other cases, interpretability is really important. What kind of trade-offs exist between efficiency and privacy? How do we mathematically define fairness and decide if a system is fair enough? How do we regulate these systems? I think these are all really important questions as we can continue to design and build these systems. So to wrap up, just a summary of machine learning. Again, just emphasizing this point, machine learning is the process of using statistics to find patterns in data sets without being explicitly programmed. There are a lot of important considerations when developing these kind of models. What kind of function are you trying to model? How do you evaluate your system? How do you check for bias? How do you collect your data? Do you have enough data? Is your data representative? All of these kind of things. And I again want to emphasize that the development of present day machine learning, where we're at today, really required insight and input from a ton of different fields and a ton of different people. And I think this is really still true today and very important that interdisciplinary approaches are key to continuing to innovate and doing so responsibly. So, computer science and math is obviously important to machine learning, but I think there's a lot of other perspectives that are really critical as well. And then I finally, just want to highlight there are so many different opportunities to get involved in machine learning. And I hope that's like the main thing you take away from this lecture is that there are so many different things that machine learning can do and so many different types of open questions that we're still trying to understand. So it's a really, really exciting field with a lot of space to get involved. So, you can do things like domain-specific applications. I've done a lot with scientific applications in physics, but there's all kinds of different things you can do. Drug discovery, cancer detection, stock and market predictions, art generation, music curation, all kinds of different things. There's tons of social good applications as well, like helping allocate resources better, understanding community needs, improving government operations, helping make government systems more efficient, getting resources to people more efficiently. There's lots of those fundamental research questions talked about, like understanding the impact of model size, interpretability, developing new types of machine learning algorithms, making sure that our systems are safe and robust, and then broader contextualization. So thinking about how we regulate these systems, how we design them, how we involve the community, how we develop safe data practices, how we prioritize privacy, and all these different things. So yeah, I think it's a really, really exciting space. And I hope after this, y'all do too, and you're excited for the rest of the week. So I put my email address and Twitter on here. Feel free to reach out to me. And yeah, I don't know if there's time for questions now. I'll defer to the organizers. But if there is, I'm of course happy to answer them.
Let's take this moment to thank Savannah for this excellent lecture. I believe we can answer a few questions if you have time. I know that, like, in terms of the program, the office hours are starting right now, but I believe we can answer a few questions. Obviously, like probably not all of them, but if you have a couple of minutes, that would be great. I see some questions in the Q&A section. Let's see.
Yeah. Would AGI mirror concepts such as assimilation and accommodation according to Jean Piaget? So unfortunately, I do not know exactly what that means. I'm not familiar with Jean Piaget. So yeah, unfortunately, I can't answer that unless you provide maybe more information. So sorry about that. AGI helps a computer understand a human's line of thinking. So AGI, artificial general intelligence, is more kind of a goal or descriptor of like the type of intelligence that we want a computer to approximate or exhibit. It's not something that I would say like exists right now. It's not a specific algorithm or a specific paradigm, but it is kind of a goal that some researchers want to get to. That would be a more closer kind of model of how humans actually think than the way we do machine learning right now. What are the AI for social good use cases to think some machine learning algorithms to apply? Yeah, so there's a ton of different stuff in the social good space. So something that I work on personally is understanding public health needs. So we did a project looking at doing effective mobile health resource routing. So if you have like mobile health vans that can kind of drive around and do pop-up clinics, what areas need that kind of help the most? So we looked at a lot of different kinds of data like health insurance, distributions, actual like infrastructure for accessing hospitals. So if you're in a city, like public transportation from different areas, if you're in more rural areas, like actual road infrastructure, the number of doctors and like availability of care in different areas, the prevalence of different diseases, people who need, assistance, who maybe don't speak English fluently, or who don't have access to the internet. And we kind of use all of that information to help do efficient routing. So that's just one example. There's tons of different things you can do. We mentioned satellite imagery briefly. So there's a lot of work doing like disaster response with computer vision. So responding to floods or earthquakes using satellite imagery and computer vision to know where to target resources to. There's all different kinds of things. Those are just like two examples. Great question. Let's see. Would pursuits and tools and research teams differ from a more corporate engineering team? Yeah, that's a great question. So definitely different types of spaces definitely do different types of AI work. So personally, I'm in academia still. So I work in an academic research lab where I really right now kind of define my own projects. And they generally don't have to be in any specific direction. If you're in more corporate structures, it kind of depends on the role. So like big tech companies have research branches as well, like Facebook, Google, they have AI research branches that are a bit more like academia. But then there's also more kind of engineering focused teams that do more product driven work. So using machine learning actually in products, doing ad targeting, or some of these different applications that we talked about. Let's see. AI technology will grow faster in countries with large populations such as China and India because more data are available for machines to learn and analyze. Is that true? That's a really interesting question. So we are seeing actually that AI is growing faster in China in particular. And it's partially what you're saying about the availability of data sets, but it's partially also like the way the government and kind of country is structured. Like there's more forced surveillance in China than in some Western countries. So that both gives you more training data and also just more opportunities to deploy machine learning. There's also a lot of investment in China in just machine learning research. I think they surpassed, like in terms of publications, surpassed the US recently. So yes, China is definitely a powerhouse in AI and machine learning research for several different reasons. Some of them are potentially concerning. But I think a key thing to think about there is, just having more people doesn't necessarily give you more data. Like, you have to have ways to collect the data, and that raises concerns about privacy, surveillance, bias, all of these things that we want to consider. So yeah, very interesting question.
So maybe we have time for just like one or two more questions.
Sure.
Yeah, thanks.
Would one difference between AI and human intelligence be that human intelligence voluntarily seek information while input is voluntarily put into the system of artificial intelligence? Yeah, that's an interesting question. So there are different types of AI systems. So like, maybe we can think about a self-driving car. So when a self-driving car is operating, it is constantly taking in information from its sensors. So it has cameras and other types of physical sensors all around the car. So that's probably the closest to, like, I think what you're saying with human intelligence. Like, we're just getting input all the time by living our daily lives. We're getting visual, auditory stimuli, and you can design kind of AI systems that function that way as well. But yeah, a lot of them, to kind of learn how to function, you're right, they have to be specifically trained. Whereas, the way that humans learn is through teaching, through school, but also kind of just through observations. Like, babies learn a lot about language just by listening to language, and we can't necessarily do that with AI right now. Like, the system can't necessarily just learn without being shown curated information and given some specific task. All right, let's see, one more question. What made you dive into the physics, logistics, and making AI? Yeah, I love that question. So I originally in college wanted to do physics research, which is why I went into a physics PhD program. And I did learn, I did do some computer science in college, and my field of physics, this particle physics, is very data heavy. So I started doing more and more data analysis, more computer science, and I learned about machine learning, like, because of that. And I realized kind of how interesting, how broad this space of work really was, and a lot of the kind of ethical concerns that I mentioned, the social good applications, those are all things that I really cared about as well. So I kind of found machine learning research as a space where I could really bring all of my different interests together. So like data analysis and coding, math, physical kind of modeling, and the social impact. So it kind of happened organically for me through my research. Yeah, awesome. Thank you all so much. It was really great to hear your questions and your insights. And I really enjoyed, chatting with y'all, and I hope you enjoy the rest of the school.
Yeah, thank you so much, Savannah. Yeah, we're super excited for the rest of the program. And if you have any remaining questions, please put them on the Discord channel. And today we have the lab sessions later in the afternoon, as well as the social event. So yeah, super excited for the rest of the day and the rest of this week. And thank you again, Savannah, for this excellent lecture. And see you all like later today. And yeah, thanks a lot, everyone. So with this, I end this session.